Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Kaze Wong with us today. Hello, Kaze.
Hello, I'm Kaze. I'm a postdoc research fellow at the Flatiron Institute.
Okay, so we are in New York on this
Yeah.
September 7th as we record this. And is there snow in New York yet?
It's supposed to snow, but I haven't seen anything yet.
Okay. I'm here in Phoenix, and we definitely don't snow. It's very rare we get a snow. It does snow in Phoenix on occasion,
Huh.
but not today. It will be a little bit too warm today, so it'll all be great.
Awesome.
Very good. And Kaze, what do you like to do for research?
So my main job in the Flatiron Institute is scientifically, it's about gravitational wave, but aside from astrophysics, I actually pay a lot of attention and care deeply about software development, machine learning algorithm building, and stuff like that.
Cool, cool. I have a little penchant for software myself, so
Yeah.
very nice. And that is going to bring us to this very awesome APJ article. It is the open access era, people. It's one's open access. You can go get it for free. Go grab a copy. Fast gravitational wave parameter estimation without compromises. In Kaze, take us away.
So this is a paper that first we put on arXiv earlier this year. I think it's around March. It's a work that done by me and a colleague at Flatiron. Actually, now I wonder why Max affiliation is off. He should be one. Anyway, so Max Easy is also a fellow at Flatiron Institute, New York. And Tom Edward, he is a postdoc fellow at Johns Hopkins. So yeah. And this paper, it's just as the topic say, we're doing a fast gravitation parameter estimation task for a gravitational wave without any compromise. So it will be more evident when we go through the paper, what are the compromise and what do we mean by that?
Right.
And the good thing about, like, one thing to stress that I mentioned that I care deeply about software. It's not just software, but open source software, accessible software. So you can see, you already find our code and everything that we do, the paper itself on GitHub, on my GitHub.
There we go. Very cool. Good. Awesome. Okay. Just some PE.
Right. So just let me know if you have any question. But so the idea of parameter estimation in gravitational wave, or really any astrophysics, is if I give you some data and I have a model about some physical phenomenon behind that it's parameterized by something. In this case, it's gravitational wave binary. So it's a binary that has two mass, maybe some spin, how far it is, where is it in the sky. And given this model and the data, now I want you to estimate what is the probability of the source parameters. Like, given the data, what was the probability distribution of my masses? Yes. So this is a task that we're given. And historically, you know, many people have, the different groups have tried to attempt this. I mean, they did a good job. And the reason why we have the infrastructure we have today, and you see all the awesome masses and correlation in those papers, is because there exists tools like Lau inference, as shown in the second paragraph, Bilby, PyCBC, these awesome tools that people develop in over the years and use in production. And they're great and robust, and they have passed through many standard tests. Yes. The only downside that people keep coming back and back is they are kind of slow, and they typically require some decent amount of computational resource to is that a question? No,
I'm just going.
To conduct these parameter estimation tasks, and it can range for one specific data. Let's say I have one event that came in a stretch of 4-second segment, so it's a 4-second time series. To estimate that, like, it could take a couple hundred cores for half a day or a day. If it is longer signal, let's say the binary neutron star, which is about 100 seconds, 128 seconds, that could take up to a week on a cluster. It's a couple hundred cores. So it's not negligible amounts of compute. And set aside the feasibility, also it's stop our workflow quite a lot, because you need to press a button, wait for a week to get your corner plot, and then figure out that you didn't output the corner plot and you didn't do it again. So it's not great in terms of workflow, and students suffer because of that. So it's a task that people have attempted to speed it up.
Right.
And this is actually gonna be more problematic, because at this point in the catalog that we have about 100 events, and in the future with Einstein Telescope and Cosmic Explorer, these future generation stuff, we're gonna have 10 to the hundreds of thousands or even millions event per year. So we are way over our computational budget. So multiple group trying to speed up the process using different techniques, like reduce order quadrature, which is basically take a long signal and try to compress them, but without loss of information.
Yes.
Using deep learning method to speed up the process and stuff like that. And there is various degree of success, and we can go more into detail in another occasion. And in this paper, we basically highlight an attempt that we pick a set of tricks or techniques that we like,
okay.
and we see potential, and as we go through the paper, we'll see why those are important and play well together.
Cool.
That we don't need to rely on some of the assumption that these new studies they're trying to speed the process up uses.
Okay.
So there's no extra assumption. It's really modern engineering and using emerging technique and to solve the problem, so that we have a robust and fast code to solve this problem.
Cool.
Yeah.
Very cool. Okay.
Yeah. And let's see where we are.
So we can go
to so here's like a list of the techniques that we use. There's likelihood heterodyning or heterodyne likelihood, and our waveform is differentiable. We can go into, like, later on we'll go into what it means by differentiable. It's not just differentiable, but automatically differentiable.
Yes.
And there's something called normalizing flow that we use as kind of a machine learning architecture, but also it's normalizing flow enhance instead of normalizing flow replace our sampler. Okay. And in the end, we also support hardware accelerator like GPU and stuff like that, and that's also important.
Yeah.
Okay. Right. So
cool. I'm with you.
Right. So that's the flow of some overview of the paper. Now, yeah. Again, everything is on GitHub. Like, everything that I do is on GitHub. It's open, so you can have all the source as shown, and the data set that we use is available on Zenodo as well.
Yes.
All right.
Perfect. Love it.
So, right. So before we go into all the magic tricks that we pull, let's be a little bit more precise about what exactly is the task.
Okay.
So given the ultimate object that we want, as shown in equation 1, is the following. So on the left-hand side of equation 1, we have the probability of a given, of a parameters. It could be mass, spin, how far that's denoted by theta. Yes. Given some data d, all right? So P of theta given d, all right? That's the object that we're interested in. If we get this object, we sort it. And this, according to the Bayes theorem, you can rewrite it as the likelihood. So what is the probability, which is the first term on the right-hand side on the top left, that is the likelihood, that is the probability of generating the data given some parameters. Yes. So flip them. So if there is a 30 solar mass black hole, how would the data look like? That's basically the first term. The second term is the prior. What do you think is the distribution of mass look like? So we know pretty strongly mass cannot go to negative. So as it's gone away from Earth and stuff like. So that's your prior. That's your prior information. Okay. Good. And in the denominator is something called the evidence, which is like the probability of this data happening. And in parameter estimation, this particular term P of D is not so important. But when you compare different model, the evidence becomes very important. Yes. But you can see all the dependence of theta goes into the numerator, and which is most of the engineering effort goes into. Okay. Cool. And I'm with you. Yeah, equation 2, it's a particular form of the likelihood that we've chosen. So that is the log likelihood that we've chosen it to be a Gaussian likelihood. Why Gaussian? Gaussian is usually the first thing that you can write down. And actually, the real data is highly non-Gaussian. We have glitches all over the place.
Yes.
And there's all sorts of different process. But our experimentalists and data characterization team did a great job in removing anything that is non-Gaussian. And we hope that we believe them enough that we know the data that we're given to estimate the parameters is reasonably Gaussian, that we can use this particular equation. So what's the likelihood saying is the law probability of generating a particular data basically follows this bracket, the inner product between these two terms. So what are these two terms? Like if you look at d minus h theta, so h is a particular model that you can have,
Okay.
Let's say given GR and given the mass is a certain number, 30 solar mass, what would be the predicted real signal look like? So if you take the data, you subtract the signal, what's left? That's the noise.
Okay.
So this is like basically saying the noise distributed Gaussianly. So that's equation 2.
Got it.
And that's the model that we use. And the complexity of here of building this, I mean, it's Gaussian, is how hard can that be? So it turns out the complexity goes mostly into h of theta, which is how the waveform model would look like, and takes quite a bit of effort. It actually took Tom quite a while to code the waveforms up.
Okay.
Right. So what's next?
Next, then we talk about definition.
So this is a little bit more precise definition of what like the inner product mean. Inner product is like if you give me 2 time series, it's basically computing sort of like a correlation between them over some noise level. So if you see extra correlation over your noise level, then there's some signal to noise in it.
Yes.
So that's the idea.
Cool.
Okay, so that's really it. Given this likelihood function, now you just need to sample it. You need to evaluate it many times to figure out what is the highest likelihood, or most probable, most likely region that these theta lives in. So that's the task. So we need to evaluate the likelihood function many times. Cool. Now, if we look at equation 3 a little bit more, then we can see why this can get expensive. So equation 3 is an integral over frequency. And as we know in Fourier transform, like you can either think of it in a time domain or frequency domain. And the more sample points you have, the more expensive your integration is gonna be, because now you have more things that you need to integrate or sum over. Right. So that's why at the very beginning I said, for a 4-second segment, it may take like half a day. But for a longer segment like a binary neutron star, then you need to evaluate your model way more frequency bins or points, and then it will cost you way more in compute. Now that naturally lead us into the first improvement that we bring in, which is session 2.2, heterodyne likelihood.
Okay.
So heterodyne likelihood, or relative binning, some other group would call, it's a technique that has been developed by a number of groups, and here we basically borrow their effort. It's techniques that basically you kind of expand your likelihood in the basis of waveform. Because if you look at gravitational wave, so we don't have a figure here, but if you look at gravitational wave waveform, they're all like sinusoid. They're chirping sinusoid. And one key factor is if the parameters are similar, the sinusoid will look similar. So this similarity allows you to expand your model around a certain point, because they're smooth. It's not like if I change the parameters a little bit and my waveform becomes completely different. If that's the case, we cannot use heterodyne likelihood. But because there's a certain smoothness in the model space that allows us to smoothly expand our likelihood in the waveform domain. It's kind of like a Taylor expansion, but not really. It's something like
in principle, like there's an analogy there.
So this idea, like the precise math and the development, it's what we've written in session 2.2, a little bit lower, I think. So
here we go.
So you can see equation 4 is basically expanding
Been
So let's say H of F is a model that you want to evaluate.
Okay.
And H naught of F is a reference point that you have found earlier. So, and this reference point is found to be a high likelihood region.
Okay.
So if you like, first we run some optimization algorithm to find what is a very possible waveform, or from the search pipeline, because the search pipeline will give you like a good guess of what is a possible waveform. So given that good guess, now we can expand around that good guess, which is shown in 4. So R of F is the ratio between the waveform that you're trying to evaluate that is different from your reference, but sufficiently close to the reference.
Okay.
Okay. Let's say I give you a system of 30 solar mass. Then you have a reference around 30 and 29. That will be close enough. If it is way far off, then your accuracy may grow. Anyway, so we define this ratio, and now given this ratio, and we only take it up to like the linear order term. Now we plug this equation 4 back into the original signal to noise. We end up with a bunch of equations shown if in 5 to 6. We don't need to go into too much of the detail, but the idea now becomes there is 2 parts of the integral. So originally, when we evaluate the integral in equation 3, we need to compute the model for each frequency.
Yes.
All right. But that's pretty expensive. That's scaled linearly as your function of sample points. And if you need to keep paying this price, that's a hefty price. But the good thing about this expansion is basically we separate the integral into 2 parts. There's one part that is highly accelerating. That you need to evaluate very precisely, which has to do with H naught, your reference waveform. So after you found your reference waveform, you need to integrate that very, very precisely, just as precise as you can.
Yes.
For once. But that's good, right? Like, because you only evaluate that for once. And all the differences between the reference waveform and the new waveform that you want to compute, you're basically computing the perturbation around the reference waveform.
Yes.
And that perturbation is sufficiently smooth, as we assume above, right? Because they are close and the waveform are similar to each other. So it's a smooth integral. So you don't need to spend as much computation. But this term now we need to recompute every time. But that's fine because it's a much lower resolution. So given this trick shown in 5 and 6, basically we can compute the original integral with one term that we need to compute to high accuracy and with a lot of sample, but we only do it once. And then for other parameters, we just compute the lower resolution fraction. So that compress the number of likelihood or model evaluation that you need for each of the evaluation. So instead of computing all the sample point for every new parameters to the maximum accuracy, now for every new parameters, you just need to compute much smaller amounts of sample point. So that's reduce your computational cost.
Okay, good. Okay, I'm with you.
Awesome. So yeah, that's the first trick. This will just the computation itself. There's the accuracy that you want to hit once you set the accuracy. Usually it is at least bring an order of magnitude speed up, but usually more. Usually it's like 2 order of magnitude.
Just from the heterodyne.
Yeah, because like the heterodyne, if you think about 128-second segment, and the sampling rate of LIGO is about 4,000. And so that's 100 times 4,000, which is what, 10 to the 5. Wow. But with heterodyne, we can compress it down to like 10 to the 3. And that's pretty accurate. So that gains you 2 order of magnitude.
Cool. Very good. Very good. Okay.
So that's just on the likelihood evaluation, and others have done that. It's not a very our innovation. We use that. Now going into 2.3. It's 2.3 so that was the likelihood. If you can evaluate the likelihood faster, you can certainly do better in terms of MCMC. Now the second thing is what's the process fundamentally that we're solving in probability estimation is MCMC algorithm. For the people that don't know, it's basically a biased random walk. So imagine your likelihood surface the surface that you're trying to sample, it's like a hill. Basically, you're tossing coin, deciding where you want to go, and as a random walk, you're trying to walk around the hill. Hopefully, you ultimately walk into a region that is reasonably close to the peak.
Okay.
And that path that you took will basically tell you how wide is the mountain, and so on and so on.
Okay.
So in low dimension, people can use traditional algorithm, MCMC, just whatever people can write up, that's fine. But if you're trying to walk on a 1,000 dimension, or not even 1,000, maybe 15 dimension hill.
Ouch.
Now, we know as we go to higher and higher dimension, everything becomes more peaky and stuff. If you take a sphere and make it high dimension, most of the mass of the sphere will go toward its surface. And what does that mean? That means if you randomly toss a coin, it's very likely you toss it downhill instead of toss it uphill if you go to a high dimension, because some volume to surface area argument.
Right.
Now, but like if you're on the hill, if you're walking on a hill, you can look around you and see where the hill is going. And that it's an analogy of using gradient. If we know the gradient of the likelihood, we know where to throw our coin. And that will help guiding the MCMC to go toward the most probable region.
Yes.
So this is our contribution that, like, Tom spent a lot of effort into writing the waveform model and the infrastructure into a framework called JAX. That if you write your program, just like any traditional program that you write in JAX, and because everything in JAX know its primitive. For example, if I write down sine x, you don't need to finite difference to get the different gradient of sine x. You know it's cosine x.
Right.
So if you know every primitive in your program, then you can just replace it with the correct operators. Then you get the derivative or the gradient usually as fast as you will evaluate the function. So you don't need to take finite difference. So you can evaluate very high dimensional gradient just as fast as you would to evaluate the function. And this is a techniques that they are standard in training neural network. If you have 10,000, hundreds of millions of parameters, and you want to take gradient against all of them, then you basically need to do this automatic differentiation.
Yes.
So we implemented our waveform model in JAX such that we can take advantage of automatic differentiation and use gradient in our sampling.
Very cool. Good. Awesome.
Cool. So this is just example, like a little bit more pathological example of like how MCMC work, and encourage people who want to know a little bit more about the detail, go read it. I'm not gonna iterate too much.
Yeah, we don't need to do that here, but yes.
Yeah. And so we have tackled how to walk up a high dimensional hill. But the problem is in reality, the question that we're interested in is usually not just one hill. Sometimes it has multiple hills that we want to hop between them. Now, that is, like, in a more technical term, it's multimodality. If your posterior has multiple mode and is separated, it will take quite a lot of effort to go from one hill to another. And you can go back to the hiking analogy, which is kind of like if you're on one hill and you want to go to the other, and you're only allowed to take local move, what do you need to do? You need to first go down a hill, which, MCMC doesn't like to throw a coin down the slope because you're trying to go to a high place. So it's very unlikely that you go down first and go up another hill. And to really transverse between them, you need to do this couple times. So you can imagine if your hills separate far away enough, or the mountains separate far away enough, it's going to get very inefficient. Now, this is where our main innovation comes in, is use something called normalizing flow. Now, 2.4, it's going to go into more detail of normalizing flow and how it's built. But without going into too much detail, it's a machine learning technique for us to generate, to try to learn a distribution. Now, I can go into infinite detail, but for the listener that it's not very familiar with this, think about this in a very fancy histogram that scales well into a high dimension, or kernel density estimator, Gauss kernel density estimator. So it's just a fancy way that you can learn way more expressive. So if you like have histogram, they're great, right? You give in some point and you histogram them. The problem of histogram is you need to store a lot of bins, and as you go to higher and higher dimension, you quickly run out of RAM.
Yes.
And normalizing flow is a technique, a neural network technique that deals with high dimensionality, and it can learn very wacky distribution. If you give it two moon separate, it can still learn.
Cool.
So instead of just walking around using whatever traditional MCMC kernel, we simultaneously learn what is the global landscape. So instead of like one person hiking up the mountain, we let multiple people hike up this mountain and let them communicate. And once they can communicate, they can kind of estimate the height and all that. And the detail of that algorithm, it's in 2.4. So not only people can hike up a mountain, now they can teleport between the mountain. So it become much more efficient. And the pseudocode and the whole exact algorithm, it's written in equation 11 and in this session. And I think it's pretty pedagogical. And actually on my YouTube channel, I have a video explaining in a minute what normalizing flow is. Maybe later I can send a link so people can find it.
I'm going to put a link in the video down below.
Yeah.
So I do have one. I'll put a link to your YouTube question. So I do have a question here. So the Jacobian here, this is coming from the autodiff.
Say again?
The Jacobian in equation 11.
Yeah. I mean, like, so it comes from autodiff, but also like so in building a normalizing flow, you need to choose the transformation to use to build a normalizing flow. So it could be it's a design transformation that we have that we know the Jacobian that can be computed very easily.
Yes. Okay.
Yeah.
Cool.
Yeah. So right, that's also like is one of our biggest secret sauce, because if you look at a gravitational, which later we'll see, the gravitational wave result, they can be multimodal, and then this really helps.
Okay.
Good. And the final piece of secret sauce is because we've written our program in JAX, and actually it comes with the support of accelerator, because JAX is actually open source Python package that it's supported by Google and developed by Google for somewhat neural network adjacent workflow. So they really need to leverage GPU and all other accelerator. So they build it into the package. Cool. And if we don't need to do too much. We don't need to write our custom CUDA code we didn't spend a lot of engineering effort in making that. It just comes with however we build the code. So now it can use many GPU cores at the same time to evaluate. And if we remember, like the multiple mountain analogy, you need multiple people hiking on the multiple mountain. So if you have GPU, that means that you can run a lot of these people, like, you know, like these walkers walking around your posterior. So that also help. And it's all this ingredient working together that give us the performance. And all of these does not rely on specific assumption that you assume for a particular problem. It's really how do we use modern compute like GPU, learned proposal or gradient. So none of these take shortcut. And that's what we meant in the title, that we don't really have any compromise.
There you go. Very good. Awesome.
Right.
I'm with you. Very cool. And congratulations.
It's a work that I'm actually proud of. So that's good. Right.
Very nice.
Oh yeah, like this highlight here is cluster cost GPU. We can evaluate in the integral. We can evaluate 10 to the 9 like times of our waveform on different frequency, different parameters. And if you remember what I said, you know, 128 segment, so 128 second segment, and 4K sampling, it's about 10 to the 5 samples. So we can actually evaluate 10 to the 4 we can iterate over 10 to the 4 times segment and every second. And that's way more than what, you know, people had before.
Very cool.
Yeah.
Very nice.
Beautiful. Right.
Okay.
Awesome.
Now we're gonna do some specifics.
Yeah. So yeah, this paragraph on the left is just saying that it's really all these component coming together and give us the performance. And it was just talking about that.
Yeah.
So to test our code, now we're getting into result territory.
Yes.
So before we deploy this to real data, we need to make sure that we're like self-consistent first. So what we did is we lay out whatever setting that we did here, that we generate a bunch of fake data as realistic as possible. And then given the synthetic data, we're trying to throw this parameter estimation code on it and ask what is the parameters, because we know the true answer.
Right.
And when we recover an answer from the parameter estimation code, and we know how often we're correct.
Yes.
So figure 1 is showing whether we like the results of whether we're being robust. So on the x-axis is I believe is the confidence level for a particular posterior. So we can just focus on one. I'll explain. We don't need to look at all the color, but really let's say the first one, chirp mass, one of the parameters that we care. So the parameter estimation code doesn't just give you one number; it gives you a posterior or probability distribution. What is the possible mass, like chirp mass, for this particular event? Now, what does that confidence interval mean? The confidence interval mean if it is a 90% confidence interval, it will say like if you are if you have a certain event, this is 90% of the time that if you do this 100 times, 90% of the mass will land in this region. Okay. So I'm 90% confident that the true result is within this region. It's still okay to have 10% outside. That's the definition of confidence level. So basically x-axis is that it's as you scan over your posterior, what's the confidence level? Now, if your pipeline of your code is unbiased, then the true value should be consistent with whatever definition of confidence level. That means your true value, if it should have 50% of the time staying within the 50% confidence interval.
I'm with you.
Right. And then we repeat this experiment, like I think we said in the paragraph below, is about 1,000 times. So for 1,000 times, maybe 50%, like 500 of the injected, like the true value, 500 of them should lay within the 50% confidence. So, and that translates to this plot, that is, if your code is unbiased, things should lie along the diagonal.
Yes.
And now things lies along the diagonal. So our code is unbiased. Actually, these are not all line, and there's pretty tight, but actually the blue band is given 1,000 events. What is the allowed fluctuation just by fluctuation? Statistic. And we lay well within that fluctuation range for all the parameters that we care. So that's great. This is to show our pipeline is not biased up to 1,000 events. Maybe if we keep having more, finally we see some bias, you always have a limitation somewhere. But in the near future, we don't have to worry about that, because 1,000 event is way more than what we have now, and it will be enough for the coming decade.
Cool. And I want to point out one thing about this figure caption, because I never actually seen it before, so this was new to me. I learned something. This little pencil symbol down here is a link to a Python script. There we go. You can see it down there. It goes to your GitHub site, and it likes to ppplots.py. So I'd never seen this little icon here before.
Yeah. So this manuscript we would prepare with something called Show Your Work. And I really it's something developed here at CCA by a former postdoc, Rodrigo Luger. That we believe everything that we write in a manuscript should be reproducible. And this Show Your Work package basically helps you to manage that. So the entire manuscript, the figure, and the script to generate a figure are linked in the paper. So if you click on that link, it will bring you to a GitHub repository that you can find the script and reproduce this figure exactly.
Nice.
Yeah. So this is a thing that we believe fundamentally in CCA.
Cool. I just had never seen that before in an APJ. I thought it was wonderful. Very cool.
Yeah.
Okay.
Practice.
So, all right, so now we have an unbiased where we know we can get back out what we put in.
Yeah. But that is, simulated data, and we always need to stress test our pipeline in real data. So that's what's the following part of the paper it's about. We
events.
scroll down. Yeah.
Mm-hmm.
These are just the configuration. Yes. Right. Like we talk about how quick this is and stuff like that. And 3.2, together with a figure that is probably comes later.
Okay.
We show how so here we're quoting the number that we use to generate a figure later and how quickly we can do that.
Yes.
And because we put this in the first word in our title, fast. So this has to be fast. And so we benchmark two important events. So GW150914 is the first gravitational wave event.
Yep.
GW170817 is the first binary neutron star event.
Yeah.
So we benchmark both of them, and we generate a certain number of effective sample. Is like basically how many independent samples you have in your posterior.
Right.
And we run it on with our code with a single GPU and some number of CPUs. And that there's compiling time and all that, but the actual sampling time is about 40 seconds.
Wow.
At the time. Wow. And actually, after that, we do further optimization. We can actually be more aggressive.
Very cool.
Yeah. And the figures later is just to show they are similar. So I think this is actually maybe like the last iteration, like the figure never get updated, because we have some data conditioning slight discrepancy, so they're not exactly on top of each other, but they're pretty close. So the blue line, the histogram, is the result from our code. The gray shaded region is the reference code that people use. And you can see there are quite a lot of unique feature in these corner plots. So for a reader that's not familiar with corner plot, this is basically the 2D distribution for each of the parameter pairs and their marginal. So if you only look at the mass and the mass ratio, these are the sample. This is the posterior. This is a probability contour. So you can see there are like in I think 5C and psi. So
let's go down to there.
The 6 on the right.
1, 2, 3, 4, 5, 6 here.
Yes, this one. Actually, there's multiple islands.
Yes.
So this was traditionally hard, and people spend great deal amount of time and thought into get it. But we didn't use all those tricks. We just run it, and Flow MC, which is the normalizing flow part, took care of it and learn all this like multimodality.
Very cool.
And yeah. So we show this for GW150914, and in figure 3 we show this for GW170817. So the point of these two figures is like it works on real data and a variety of real data. Oh, like that correlation, the multiple island, you can see it a little bit more clear.
Yes.
Here in GW170817.
Yep.
Yeah. So we build the algorithm. We show that it works on synthetic data very, very quickly. And also, but it also works on real data. And we really stress that it has to work for real data.
Oh, absolutely.
We care deeply because, yeah.
That matters. Very cool. Very cool. Very cool. Yeah. And we're going to hold on the future here. We'll talk about that in a second. Very awesome. Very nice. Okay, it's very cool. All righty. Very nice. Kaze, thank you so much for walking us through your very awesome APJ article.
Thanks for having me.
I love it. And you do talk about it a little bit there, but I want to bring it out here. Where do you think we go, let's say, over the next couple of years with this technique and the data? Is there things that could be improved in the technique even more so we can get it, let's say, another factor of 2 efficiency? Is this going to be installed on one of the LBK pipelines as part of their normal processing, etc.? And so just sort of where do we go from here, both in the software and on the GW side?
Yeah, so I'm actually very excited about the future development prospect, and I think I have gotten quite a lot of email and message saying that like this is great work, we want to use the code. And at the very first iteration, we're trying to make the paper and make sure that it's performant. But now it's more about making it user-friendly enough that people can actually use it.
Yeah.
Other than, I know how to tweak all the knobs. But
I don't.
The user won't know, right? So we're working on toward making really smooth top level user API for others to use it. Not only just LVK, because the gravitational wave community is bigger than the LVK. And we want to empower the user to, if they want to have an extra waveform model, we'll show them example. How do you do that? Some people actually care about, oh, I have the fiducial gravitational wave model, but what if I have this modified gravity? There's a paper that is going to come out relatively soon that using our code to do, they trying to do tests of GR. So they need to introduce some non-GR parameters and trying to recover them. And we have shown seen success there. So I think making it more user-friendly and flexible, and in my words is I want it to be extensible, making the code extensible by normal user. Instead of giving people like a one-button solution, I want to have the community understand what we're doing, understand some of the limitation and assumption that goes into what is parameter estimation really doing and how they should use it. And then they can take it away, right? Like they can use it to do their help their workflow. That's what we want to bring, is to make this tool user-friendly and extensible by the community. And yes, we like Max is actually in LIGO, the LVK collaboration. So he is we're working with the collaboration to make this adapt to at least one of the pipeline, because the problem with having pipeline is like you don't want to throw away the old one, because it's always good to have multiple cross-check. But maybe this one can be the rapid one. If we fall flat somewhere, then we have multiple cross-check.
Right. And if you find something interesting, you can always go back and double check it with Bilby or something.
Exactly.
So yeah, very cool.
Right.
Super. The very nice piece of software. Congratulations.
Thank you.
I really look forward to seeing this one grow and develop and take root. So awesome.
Thank you.
And that'll do, everyone. And I hope this made your astronomy day, your open source astronomy day, just a little bit better. And we will see you on the next one. Bye-bye.
Bye-bye.